Thank you for listening to my Deep Learning and AI Summative Assessment presentation. This presentation explores how deep learning could enhance and replace our current machine learning approach to source site prediction and sales forecasting. The agenda for this presentation is as follows. The executive context will set out the objectives for our analysis. The current machine learning model will look at efforts so far. Next, we will explain what improvements are needed, followed by how we can use deep learning techniques to mitigate these problems. Next, we will consider the strategic outcome we would hope to see and why we think it is likely, followed by the ethical concerns, deployment hurdles, and what the future looks like in this project. Finally, we will discuss what we can conclude from our findings so far and why we are keen to develop a deep learning strategy as an integrated marketing agency. This project explores how to evolve from the current heuristic model for store location selection to an evidence-based approach. First, using my machine learning model consisting of principal component analysis, k-means clustering, and random forest algorithms, and now also evaluating how a wide and deep learning model might improve that process. I'll assess what this approach adds, what challenges it introduces, and how it might perform in real-world business terms. Our current process relies on intuition and experience, which, while valuable, can be biased and unscalable. Hub, as an integrated marketing agency, has several large clients who use both our marketing and data services. One of our biggest clients relies on our strategic advice services to pick out new stores based on extensive experiential analysis of their key demo, the 65 plus age bracket, using heuristics, spreadsheets, and intuition. Strong growth and a focus on data strategy at Hub has led calls for a more informed method for forecasting both store performance and to help inform where to put the next several stores in relation to the current for our largest client. Store misplacement could be a costly mistake, so data-driven decision-making is required going forward. This has led us to look at two primary objectives for this. The first, to develop an evidence-based deep learning model that predicts store-level sales performance more accurately than the existing heuristic and experiential approaches, and then to apply these predictions to guide the optimal placement of the next 30 physical stores, a doubling, minimizing cannibalization and maximizing access to untapped customer demographics. Here I hope to describe the current machine learning model in development currently and the several iterative steps we've taken to get where we are. We currently use principal component analysis to reduce features, k-means to cluster those features, and random forest to predict daily sales by postcode sectors. Initially, in the preceding professional development module, we built a composite model consisting of principal component analysis, PCA, k-means clustering, and a random forest algorithm, with inputs from both demographic and sales data. The initial model detailed the top 5 PCA feature combinations that could explain 44% of the variability, and when combined with a random forest algorithm, it predicted current store performance with a difference of only 4.4%. However, this was with consistent underprediction. Further iterations have moved away from predicting the current store performance to evaluating predicted postcode sector value, whether they had previous sales or not. The attached infographic shows how the current iteration of the machine learning model works in practice. Managed with Jupyter Notebook currently, with plans to integrate with the seasonality and cannibalization models that are also in development at this time. Elsewhere, we've created a BigQuery table containing a centroid data taken from ONS plots of current postcode sector data that shows the distance between a source and target postcode up to 100 kilometers away from each other. Used in conjunction with the postcode sector prediction model, this allows us to work out what an aggregate value is for any postcode sector. In short, this means that if we were to place a pin anywhere on a map in a particular postcode sector, this would give an evaluation, depending on how many postcodes have been aggregated to it, of what the potential value of that site could be. However, the current model is brittle to external factors like store maturity, seasonality, and competitive overlap, which aren't features that have been so far incorporated. The original model iteration showed us that it was consistently under-predicting by 4%, but it did show us that beyond the 65 key demographic, there were actually 3 main clusters that were made up of 5 different principal component groups. The second iteration moved on to using this idea to evaluate variable data sets of varying periodicity to ascertain postcode sector revenue predictions for postcodes with sales and without. The most recent iteration uses that periodicity but on a rolling period basis. A fully test-trained model consistently predicts results for the postcodes with and without pre-existing sales with limited volatility. This will predict the larger glut of postcodes where there is enough of a feature basis to actually provide postcode sector analysis for that and a prediction. This table illustrates the strides the model has taken in explaining the data. However, the current rolling 4-year iteration of our model sees that we are approaching limits to what can be interpolated from the results. In its current iteration, this model performs well overall with an R-squared value of 0.88 and 99% postcode coverage, but suffers from high local variance. Additionally, it is also not currently automated. Likely, the next iteration of this model will fully integrate it into BigQuery and using Cloud Run on Google Cloud Platform, which is our platform of choice. So it can be used to integrate forecasting into future reporting suite upgrades for our client, likely with some sort of reporting card system which evaluates the predictions versus the realized actual revenue. With some of the problems already illustrated in the previous section, here we will demonstrate the value of the current model and also its limitations. The current map shows the predicted sales value for all postcode mapped out for intensity with the existing stores in red. These are the aggregate predicted sales areas up to 50 kilometers. The experiential model is well-founded and based on strong conclusions on the basis of this, as most of the existing stores were placed here on the basis of that experiential model. And as you can see, they're heavily nested in the deep blue areas where the maximal predicted sales revenue is likely to be apparent. However, it is important to note that the newer machine learning model is good at capturing only the floor value for all predictions, because it is based entirely on demographic features, but not the edge cases. Our most recent analysis of sales in week 32, the last week in which a new store was actually opened, especially when accounting for seasonality using our most recent seasonality model, showed that there was only a total difference of 7.6% from the actual revenue for that week, but fails to capture the edge cases for that week at all well, as you can see from the values there from the predicted versus actual. However, when you look at the granularity of this weekend breakdown by individual stores, you can see that the percentage difference between predicted and actual store revenue can fluctuate quite heavily at the edge cases, both in negative and positive terms. Indeed, for the new store that opened week 32, the predicted value versus the actual was over 300%. In all likelihood, the next iteration of this model will have to feature media spend, store maturity, staff training as metrics where possible. Limitations aside, the machine learning model is omitting some feature interactions which are likely crucial in explaining some edge case differences. Which brings us to the alternative, longer-term solution in terms of using deep learning techniques. In particular, we will focus on wide and deep neural networks as an alternative, which would give us the benefit of modeling well-established features in the model, whilst identifying multi-dimension hidden effects responsible for edge cases and that aren't yet accounted for, such as media spend, store maturity, and similar. The wide and deep model is designed to capture both memorized patterns and high-dimensional generalizations simultaneously. This diagram shows how categorical and continuous features are processed separately, combined, and trained using backpropagation and mean squared error, combining the strengths of memorization and generalization within the wide and deep neural network model. The wide path handles known explicit feature interactions such as postcode and tenure, and how in cases where these are easily predicted well together. The deep path learns more abstract relationships through multiple layers, discovering patterns we might not explicitly define. Both paths converge into a final prediction layer, allowing the model to handle seen and unseen cases with greater robustness. Unlike a random forest, the wide and deep model asks how a postcode's demographic feature characteristics relate to others and builds a more complete picture from all available data, whilst the random forest looks to pigeonhole features for each postcode. Here are the benefits of replacing the current model. Postcode sectors are embedded as dense vectors, so the model can understand similarities across regions, unlike random forest, which treats them as distinct. For capture of nonlinear feature combinations using ReLU, we can the experiential limitation that we currently use focuses on one or two dominant variables but misses multidimensional patterns. The current machine learning model will handle some of those interactions but lacks generalization power, which is where the deep layers in the wide and deep learning model will learn rich feature interactions and nonlinear trends. The ability to generalize to new or unseen zones is not justified using our experiential limitation, as there's no way of proving it. Struggles with unfamiliar or underrepresented postcodes is very apparent in the machine learning model given the high degree of variance that we see at edge cases, but those patterns themselves will be latent patterns that can be embedded and handle, which allows the wide and deep model to handle sparsity and novelty. Similarly, with categorical and continuous features, we can only look at the dominant categories in our experiential analysis. However, we normalize and treat all of these categories uniformly in machine learning, whilst the wide handles categorical information, whereas the deep handles numeric in separate steps to provide a better rounded picture in wide and deep. Again, the experiential limitation shows problems with scalable and future-ready iterations of itself. Whilst the current ML model will require full training and is brittle to drift, we can expect a wide and deep model to incrementally retrain itself to support the trends, seasonality, and drift caused by unknown features. In terms of explainability and insight, we can use the anecdotal power of experiential limitations and justify them, which is what has actually happened to great effect. However, some interpretability from feature importance is apparent in machine learning models, which would allow us to open up to new demographics and introduce key demos. However, a wide and deep learning model allows us to open up to the benefits of both SHAP and LIME to look at how those generalizations can actually be interpreted into hard facts, so that we can look at and visualize individual components and see why a feature is actually important. This also helps us divert away from black box problems apparent in many deep learning models. Next, we will summarize how we expect wide and deep neural networks to improve on experiential and machine learning approaches across several key forecasting dimensions. Even with strong machine learning performance, we still see postcode level errors and variability. Deep learning can help stabilize these. In terms of how it summarizes these things with principal component analysis and our random forest model, what we would hope to gain are incremental improvements in each of these key metrics on this table. For RMSE, we had anticipated a decrease in this, with the wide and deep model being capable of learning latent feature interactions responsible for our edge cases, so complex relationships between demographics, spatial clusters, seasonality, and store spend that are not accounted for currently would actually be meted in part and result in better predictions at the edge and in underrepresented postcode zones. For the mean absolute error, we should also see this fall in parallel as a result, since MAE is closely aligned to the loss function during training, in this case MSE, where we would expect tighter performance on both average error and error variance as backpropagation corrects for these edge cases. Similarly, we would hope to see improvements in the R-squared value even if albeit modestly, where we would expect the combined wide and deep branches to help capture both known linear patterns on the wide side and more abstract high-dimensional ones on the deep, reducing unexplained variance across the model. We would not see much change in the prediction coverage as this is above 99%, but we can expect that the deep branch of the wide and deep learning model would allow us to account for more complex, esoteric outer groups like those postcodes. Overall, we would hope that the difference versus actual would drop in terms of the total expected difference, as the per store, particularly in the per store predictability and reliability, with the introduction of the deep branch, which would be able to generalize across more complex non-linear categorizations. In closing, deep learning offers a more expressive modeling framework, especially when we start to incorporate richer dynamic features like storage, campaign spend, or training quality. However, its promise will only surpass the current random forest and PCA model meaningfully when it is fed more diverse and temporally contextualized data. As more features are identified and more features incorporated, the actual outputs will be sufficiently better. Deep learning is not a silver bullet for much of this. It is a more powerful tool that realizes its full potential when embedded in a wider ecosystem of enriched features and robust governance. We should be cautious not to equate architecture complexity with outcome certainty. What matters just as much as the model is the breadth and quality of the data inputs. And currently, our model is still mostly demographic, which is very good at providing a floor value for sales performance. The next gains in accuracy, whether with random forest or deep learning, will come from integrating factors like media spend, staff training levels, and store maturity curves. Next, we will discuss the ethics, deployment, and future components for making modeling future-friendly. With all this in mind, we're still in the very early stages, but we can say with a great deal of certainty that no personal data will be used beyond the ability to go and to determine where sales are located in terms of postcode and geographic basis. This leaves it currently very open to demographic bias, but we're hoping to correct for that with bias mitigation measures such as demographic weighting and explainability techniques, which avoid black box problems like SHAP or LIME. An interesting question posed by what the future holds is presented in the difference between the current machine learning model and any future wide and deep model. Whilst the ML model could potentially be improved upon with more features beyond demographics, which, as I stated before, are clearly a floor value for performance, a wide and deep model has the potential to intuit the existence of other features without knowing their exact makeup. To repeat for clarity, we would hope to be able to intuit these new features that can't be seen and actually start to determine how they make up in composition the generalized deep arm of the wide and deep model using both SHAP and LIME. In summary, wide and deep learning models can offer us a scalable, explainable path forward that moves us from a reactive planning to proactive data-led decision making. Experiential analysis to predict our sales performance has proven extremely effective up to now, but we can do more. The machine model is on a journey of extrapolating from a ever wider selection of features to improve the capture of edge cases, but again, we can do more. The potential for a wide and deep neural network model has the potential to shed light on some of the features we fail to capture with the current machine learning or experiential models, and will give us the ability to scale as necessary to understand their importance when we do. We will take this beyond demography and incorporate other metrics in the future, enabling us to develop a more rounded picture for our clients. Thank you for joining me on this presentation.